In this video, I will show you how to draw the output waveform of this given clipper circuit. After drawing the output waveform, I will show you the comparative analysis of input and output waveform using Multisim simulator. Draw the output waveform of the following clipper circuit. We have to draw the output waveform of this clipper circuit. See, here we will take the output across this terminal and this terminal by considering this terminal at higher potential and this terminal is at lower potential. Here we will be applying a sinusoidal voltage whose positive maximum will be plus 20 and negative maximum will be minus 20 volt. In the circuit we have total 3 resistors, R1, R2 and R3. All of them have values equal to 1 kilo ohm. Consider the diode built-in potential equal to 0.7 volt. See, in the circuit we have two ordinary PN junction diodes D1 and D2. As the built-in potential will be 0.7 volt, that means the diode D1 and D2 will be made of silicon. And VZ1 is equal to VZ2 equal to 5 volt. This means that we have total two Zener diodes here, Z1 and Z2. That means the Zener voltage of the Z1 and Z2 will be 5 volt. That means when the Zener diode will be in Zener breakdown region, we will replace them with a voltage regulator or a constant voltage source whose value will be 5 volt. Now I will show you how to draw the output waveform of this clipper circuit. Let's say our input is going through its positive half cycle. During positive half cycle, this terminal will be positive and this terminal will be negative. The positive terminal of the applied voltage will be connected with the inside of the diode D2 and the negative terminal will be connected with the P side of the diode D2. As a result, you will see the diode D2 will be in reverse bias during this positive half cycle. As the diode D2 will be in reverse bias during the positive half cycle, we can replace that with an open circuit. If we replace the diode D2 with an open circuit, our circuit will look like this. See, that means during positive half cycle, the current through this branch will be equal to 0. As there will be no current flow through this branch, we can ignore this branch from the circuit or we can remove this branch from the network. So if I remove that branch from the network, we will left with only this branch. Now see, the positive terminal of the applied voltage is connected with the P side of the diode D1, N side of the Zener diode Z1. The negative terminal of the applied voltage is connected with the P side of the Zener diode Z1 and N side of the diode D1. That means during positive half cycle, the diode D1 should be in forward bias due to the applied voltage and the Zener diode Z1 should be in reverse bias during the positive half cycle. Now see, if we want to conduct the current in this direction during positive half cycle, both the diode D1 and Z1 should conduct, and they will conduct only if the diode D1 is in forward bias and the Zener diode Z1 is in Zener breakdown region. Therefore, how much voltage we will need to put the diode D1 in forward bias and Zener diode Z1 in Zener breakdown region? See, if I denote this terminal as A, this terminal as C and this terminal as B. To put the diode D1 in forward bias, we will need a voltage equal to 0.7 volt at least. And to put the Zener diode Z1 in Zener breakdown region, we will need a voltage at least equal to Zener voltage VZ1, which is equal to 5 volt. Therefore, we will need a voltage of around 5.7 volt to put the diode D1 and Zener diode Z1 in conduction simultaneously. Otherwise, we will not get any current flow through that branch. So there will be a threshold for the current conduction during positive half cycle, that is equal to 5.7 volt. Let's say this is that margin, 5.7 volt. When applied voltage Vi will be greater than 5.7 volt, we will get sufficient voltage to put the diode D1 and Zener diode Z1 in corresponding bias simultaneously. Therefore, we will get current through the diode D1 and Zener diode Z1. That means D1 and Z1 will conduct. And when Vi will be less than 5.7 volt, we will not get 5.7 volt between these A and B terminals. Therefore, the diode D1 and Z1 will not conduct any current. As they will not conduct any current, that means the diode D1 and Z1 will act like open circuit, because we know there is no current flow in an open circuit. So let me consider the two cases when Vi is less than 5.7 volt. Vi is less than 5.7 volt, so we will not get sufficient voltage to drive the diode D1 in forward bias and Zener diode Z1 in Zener breakdown region. Therefore, D1 and Z1 will not conduct any current. That means during positive half cycle, as long as Vi will be less than 5.7 volt, I in the circuit will be equal to 0. As there will be no current flow through this branch, we can consider this portion of the circuit like an open circuit, as there will be no current flow. Therefore, the voltage across this resistor R1 will be equal to 0, IR1 ohmic drop across this resistor R2, which will also be equal to 0. Therefore, you will see there will be no voltage absorbing element in this circuit during Vi is less than 5.7 volt. That means as long as Vi will be in this portion, our output voltage will be equal to Vi, or Vo follows input voltage Vi, or Vo has the same wave shape as the input voltage Vi. So if this is our applied voltage Vi with positive maximum plus 20, let's say this is that transition voltage of 5.7 volt. In this region, our diode will not conduct D1 and Z1. As a result, Vo is equal to Vi. From this point to this point, our input is changing like this, so our output will follow input voltage. From this point to this point, our input is changing like this, so our output will follow the input voltage. There is another case when Vi is greater than 5.7 volt. That means I will be talking about this region. As long as Vi will be greater than 5.7 volt, we will get sufficient voltage to drive the diode D1 in forward bias and Zener diode Z1 in Zener breakdown region. As a result, we will get current through this circuit. When the diode D1 will be in forward bias, we can replace that with its constant voltage drop model or voltage source of 0.7 volt. And when the Zener diode Z1 will be in Zener breakdown region, we can replace it with a voltage regulator or a constant voltage source whose value will be equal to VZ1 or 5 volt. So if we replace the ordinary diode D1 and Zener diode Z1 with corresponding equivalent circuit, we will get a circuit like this. Okay, now see, we will get a constant voltage of 5.7 volt as long as Vi greater than 5.7 volt between this A and B terminals. Now see, here Vi is changing sinusoidally, or applied voltage is a sinusoidal voltage. As Vi is changing sinusoidally, we have resistance in the circuit, two resistors of 1 kilo ohm and 1 kilo ohm. Therefore, as V is proportional to I, or I is proportional to V, we will get sinusoidal current I in the circuit. As the current will be sinusoidal. Therefore, the voltage across the resistance R2, which will be IR2, will also be a sinusoidal voltage. That means when Vi will be greater than 5.7 volt, our output voltage VO will be sinusoidal voltage. Now, what will be the value of maximum output voltage? See here, input voltage has its maximum value of Vi is equal to 20 volt. Vi is 20 volt, or Vi max is equal to 20 volt. When Vi will be at 20 volt, we will get VAB across this terminal to this terminal, which will be equal to 5.7 volt. Therefore, if we subtract 5.7 from 20 volt, we will get 14.3 volt. That means when Vi will be equal to 20 volt at this point, we will get 14.3 volt across this R1 and R2 resistor. And see, both of the resistor has same value. Therefore, the voltage across this 1 kilo ohm resistor IR2 will be equal to 14.3 divided by 2, which will be equal to 7.15 volt. So IR2 max will be equal to 7.15 volt. As a result, our VO max will be equal to 5.7 plus 7.15, which is equal to 12.85 volt. And output voltage will change sinusoidally because we will get sinusoidal current, which will produce sinusoidal voltage IR2, and the maximum value of output voltage will be 12.85 volt when Vi will be equal to 20 volt. And I will show you this result during the simulation. So this is our maximum point, 20 volt. Let's say this is our 12.85 volt. From this point, let's say this is our 5.7 volt. So our output voltage will be maximum at this point, and it will also follow the sinusoidal wave shape like this, for example. Okay, so this will be our output waveform during positive half cycle. Now consider the negative half cycle of the applied voltage. That means I am talking about this portion of the input voltage. During negative half cycle, this terminal will be negative and this terminal will be positive. The negative terminal of the applied voltage will be connected with the P side of the diode D1, and positive terminal will be connected with the N side of the diode D1. That means the diode D1 will be in a reverse bias, and we know that when a diode is in reverse bias, we can replace that with an open circuit. So I will replace the diode D1 with an open circuit. If I replace the diode D1 with an open circuit, you will see the current in this direction will be equal to 0 because there is no current flow through an open circuit. That means we can remove this entire branch from the network, or we can ignore this branch from the network. So after removing the branch, I will get a circuit like this. Now see, the negative terminal of the applied voltage is connected with the N side of the diode D2 and P side of the Zener diode Z2. Positive terminal is connected with the N side of the Zener diode Z2 and P side of the diode D2. That means Vi is trying to diode D1 in forward bias and D2 in forward bias and Zener diode Z2 in reverse bias. Now see, if I want the current to flow through this branch, we have to keep the diode D2 in forward bias and the Zener diode Z2 in Zener breakdown region. Let's say this is our D point, this is P point. If I want to operate the Zener diode in Zener breakdown region, I will need a voltage which will between this terminal to this terminal, which will be equal to -5 volt. If I want to keep the diode D2 in forward bias, I will need a voltage of -0.7 volt between this E and A terminals. That means I will need a total -5.7 volt between this terminal to this terminal. If I want conduction through the diode D2 and the Zener diode Z2, so there will be a threshold for the current conduction through this branch. Let's say this is -5.7 volt. This region will indicate when Vi is greater than -5.7. This region will indicate when Vi is less than -5.7 volt. Now see, when Vi is less than -5.7 volt, we will get -5.7 volt between this terminal to this terminal. As a result, the diode D2 will be in forward bias and our Zener diode Z2 will operate in Zener breakdown region. That means both of the diodes D2 and Z2 will conduct. Therefore, I will get current conduction. But when Vi will be greater than -5.7 volt, we will not get sufficient voltage of -5.7 between this A and D terminals. Therefore, the Zener diode Z2 and the diode D2 will not conduct any current. As a result, there will be no current conduction, so the Zener diode Z2 and the diode D2 will act like open circuits. Now consider when Vi is greater than -5.7. That means I am talking about this portion. You will see the Zener diode Z2 and the diode D2 will not conduct. That means we will not get sufficient voltage to drive the diode D2 in forward bias and Zener diode Z2 in Zener breakdown region. So they will not conduct. As a result, the current in this direction, I will be equal to 0, and the diode D2 and Z2 will act like open circuits. So I can remove diode D2 and Z2 as there will be no current flow. Therefore, the ohmic drop across the resistance R3, which is equal to IR3, will be equal to 0. IR1 will also be equal to 0. As a result, there will be no voltage absorbing element during this Vi greater than 5.7 volt. Therefore, our output voltage will be equal to Vi, or output follows the input voltage, or output voltage has the same wave shape as the input voltage. I will show this during the simulation. So let's say this is our -5.7 volt. I am talking about this region. From this point to this point, our input is changing like this, so our output will follow input. From this point to this point, our output will follow input voltage. So input is changing like this, so our output will follow the same wave pattern or wave shape. Now consider when Vi is less than -5.7. That means I am talking about this portion of the applied voltage. In that case, we will get sufficient voltage to put the diode D2 in forward bias and Zener diode Z2 in Zener breakdown region. When Zener diode will be in Zener breakdown region, Zener diode will act as a voltage regulator. As a result, we can replace it with a voltage source like this, whose magnitude will be equal to Vz2. Here Vz2 is equal to 5 volt. This will be positive terminal, this will be negative terminal. As D2 will be in forward bias, we can replace it with its constant voltage drop model like this, whose value will be 0.7 volt. This will be negative, this will be positive. So if I replace the diodes with their equivalent circuit models, I will get a circuit like this. And I am talking about this portion of the applied voltage when Vi is less than -5.7 volt. The diode D2 will be in forward bias, so we can replace that with a voltage source of 0.7 volt like this, and the Zener diode Z2 will be in Zener breakdown region. As a result, we can replace it with a voltage source of VZ2 or 5 volt like this. Okay, so this will be our circuit. This was our A terminal, this was our D terminal. Between A and D we have this 0.7 volt and this 5 volt. So we will get minus 5.7 volt between this A and D terminal as long as Vi will be less than 5.7 volt. Now see, in this region our Vi is changing sinusoidally. As we have resistors of R1 and R3 in the circuit, we will get sinusoidal current. Sinusoidal current will create a sinusoidal voltage drop IR3 across the resistor R3. As we are taking the output across this terminal and this terminal, you will see our output voltage will also be sinusoidal. This was positive, this was negative terminal. Now what will be the maximum value of negative output voltage? Now see, when our input voltage Vi is at its negative maximum or minus 20 volt, you will see I will get minus 5.7 between this A and D terminals. Therefore the rest of the minus 14.3 volt will be divided across the resistor R1 and R3 using voltage divider rule, as they are sharing the same value of 1 kilo ohm and 1 kilo ohm respectively. So I will get minus 7.15 volt. That means IR3 max will be equal to minus 7.15 when Vi will be at minus 20 volt. In that case, our output voltage max or negative maximum voltage will be equal to, from this point to this point I will get minus 5.7. Across this R3 I will get minus 7.15. So I will get minus 12.85 volt. So our negative maximum in the output voltage will be minus 12.85 volt. Our output voltage will be a sinusoidal voltage because IR3 is a sinusoidal voltage which is created due to the sinusoidal current in this direction. Okay, let's say this is minus 20 volt. So our minus 12.85 will be, let's say here, minus 12.85. Our output voltage should change sinusoidally. This was minus 5.7 volt. So our output will look like this. You will see the clear picture of output voltage in the Multisim simulator when I will show you the simulation. Okay, so this is our circuit in Multisim simulator. You will see the red waveform will indicate the input and green waveform will indicate the output waveform. Now if I run the simulator, you will see this will be our input waveform and this will be output waveform. Input is in the channel A and output is in channel B. Now see, initially both red and green waveforms are changing same way. That means our output voltage is following the input voltage. Okay, after that you will see when Vi is at its maximum value, let's say 19.964 volt, our output is equal to 12.795 volt, which I got 12.85 volt when Vi is equal to 20 volt. See, from this point to this point our output is following the input waveform, and when input is at its negative maximum, let's say minus 19.938 volt, our output is equal to minus 12.783 volt. And see, our output voltage is nearly sinusoidal, and I got the negative maximum equal to minus 12.85 when Vi max is equal to minus 20 volt. Okay, so this verifies my circuit analysis.